So right here, what I'm looking at, these are the notes for the lesson we just finished. If you weren't here, I posted the lesson on your Google Classroom. Now, that lesson that I posted is like 4 days worth of me teaching. So the video is like 2.5 hours long. So you might have to fast forward to the parts that you missed. But it is posted on your Google Classroom. We were asked to find an equation of that table of values. And the equation we came up with was x equals 2 to the y power. Right? Do we remember that on B? Or number 2? I don't remember what the problem was. It was the second question, right after the table. Everybody see that? Looking back at that? Okay. So, what they're doing here, they're going to teach you how you can rewrite this as a logarithmic equation. Because every equation that we've written, whether it be for a line or for a quadratic or a cubic, square root, cube root, we always like to have y by itself. Because y is the same thing as f of x. So in our equation, I want to get y by itself. Well, why is y not by itself? Well, this is confusing.
Because it has 2.
But what's the 2 doing? Yeah, it's got a 2.
It's raising it.
That's not multiplying.
It's raising it to another power.
Well, y is not being raised to another power. Y is the exponent.
Oh, I didn't think it was exponent. It looks like just 2y.
How do I get a y that's in the exponent out of the exponent?
It's hard.
We need a new tool. You don't have a tool that can do it. I can't add, subtract, multiply, divide, square root, cube root. None of that works. One of my classes, it must have been 6th period yesterday, said to take a y root. All right?
That was me.
Is that you? Okay, well, I couldn't remember. So what would happen? What would happen if I took a y root?
You explained it yesterday.
Well, the y root of 2 to the y, those would cancel. The right side would be 2. The left side, I would have the y root of x. Do you feel any closer to getting y by itself? No, I feel farther away, right? I mean, that's the disaster.
You probably click
So,
that log E X button on your calculator.
we are going to use a logarithm. So this is my base, this is the exponent, and this was the answer. Okay? So if I have to rewrite this, the most simple way to write it, we could write this as log base of 2 of my answer is equal to the exponent. Log base 2 of x would equal y. Now again, just like with exponentials, remember I showed you there are several different ways that you could write an equation for a graph that all were correct. Like where we had 2 raised to the x plus 3. Remember we changed that to 2 to the x times 2 to the third. 2 to the third is 8. So it became 8 times 2 to the x. Well, that's the same thing. This is not the only way we could get y by itself. This is just maybe the most efficient way. Is we could take a log base b of the answer equals the exponent. I personally don't normally write logs with a base of 2 because the calculators that I had
It's log base 10.
only had log base 10 or log base e. And we're not talking about what e is yet. That's coming. But just know I could have a different base here that would make this different, but it could still be the same thing. Okay, they're equivalent forms of this. So you guys are going to have to become very good at switching between these two forms, from exponential form to logarithmic form. Okay? So you've got to feel comfortable enough doing that. So like, right here, if I have x equals 2 to the y, I have to know this is log base 2 of x equals y. Or, if I had this, I could rewrite it as 2 raised to the y equals x. Right? So either way, you've got to, I don't have a good way to tell you how to memorize it, other than you just got to do it. So again, you can see that they're calling this logarithmic form. This is exponential form.
And logarithmic form is the one that's going to actually help us get the answer. Right?
Sometimes. Well, we're going to have to almost convert back and forth on every problem. Most of the time, to get the answer, if it starts in exponential form, we're going to have to rewrite in logarithmic. Then we're going to start working in logarithmic so much that we're going to have to get it out of logarithmic form into exponential form. It's almost always, it needs to be in the other form.
So this is going to be size.
It's different. It's very different. All right. If I write just a log and I don't write a base, if I wrote log of x equals y, that's correct. If there is no subscript, assume that the subscript is 10. Right, that's what that says right there. So log on its own is the same thing as log base 10.
I remember doing this last year, but it was not as complicated.
Yeah, you're gonna be okay with some of this, and then it's gonna
Snowballing.
yeah, this eventually starts blowing people's mind, and it's normally the worst section that we have. So
Well, I've not really done good on any of them, so this is not good.
so what I'm telling you is stay on top of it right now. Stay on top of it right now.
I thought I did the worst on the last test, but it was that I actually made a B on the test. So I don't know how that happened.
Okay, here's the next one.
Just like, I thought I made a
If the base is e, so log base e, we can write this as natural log. Log base e is the same thing as the natural log.
What is it?
E,
It's like pi, it's not,
it's like pi because it's an irrational number.
it's like 2 point something, not 3.4.
Here is what's important, or why e is so important in calculus. E to the x. If I were to find the instantaneous rate of change, so the slope of a tangent line, right? The instantaneous rate of change of the graph of e to the x, no matter which point I choose, the answer is still e to the x. That is what makes e such an important number. It's the number for which the instantaneous rate of change at that value is that value. So that's kind of like, you're not quite ready for that. Here, let's graph x squared. Okay? So at x squared, at 1, what is the instantaneous rate of change? You may not know. I know at 1, the instantaneous rate of change is 2. The slope of this tangent line is 2. So at 1, the instantaneous rate of change is 2. Well, if I plug in 1 here, I would get a value of 1, right? So the y value here is 1, but the instantaneous rate of change is 2. They're not the same. You see how they're not the same? The y value is 1, the instantaneous rate of change is 2. So for e to the x, which is an exponential graph that looks like this, right? When you looked at 2 to the x, 3 to the x, e to the x is the same thing. E is like 2.7 something. I don't know. So it's just like my 2 to the x, 3 to the x graphs. If I were to pick the point 1, so e to the x at 1, if I plugged in a 1 here, this would be e to the first power. So the y value is equal to e. You follow what I'm saying? If I plugged in a 1, like right here, I plugged in a 1 for x squared. What is 1 squared? 1. You have to take my word for this, because you don't have the tools to find this yet. But I promise you, the instantaneous rate of change at 1 is 2. And they're different.
How?
You don't have the tools to do this yet. Calculus. I took a derivative.
Oh, co-couples do that.
You have to do the limit as x approaches h of f of x plus h minus f of x all over h. You've seen all this before. This is the difference quotient that you saw. We've been working on limits. I mean, I'm building you up to understand this, but you're not there yet. And I don't have time to explain it. You just got to trust me. At 1 for x squared, the instantaneous rate of change is 2. But the y value was 1. So here, if I plug in 1 to e to the x, e to the first power is e. I promise you, if you were to find the instantaneous rate of change of e to the x at 1, it's also e. So the slope of this tangent line is also e. So the slope of the tangent line and the instantaneous rate of change are the same at 1. It's not just at 1, it's at any point you choose. So if I go to 2, what would be the y value at 2? So e to the x at x equals 2. This would be e to the second is the y value. I have to promise you again, if you found the instantaneous rate of change, it's also e to the second. The slope of that tangent line at 2 is the same value as the y value. Again, kind of confusing. It's not going to be a big deal to you yet, but that's why e is so important. It's a great thing to take a derivative of in calculus because we know what the derivative is very quickly.
So
it's the same thing.
The tangent line is the same as the y value.
No, yes. The slope of the tangent line is equal to the y value. Only with e to the x.
So like say if it's 100,000 million up there, then
If
the
the-
slope's going to be 100,000 million.
The slope at the tangent line at that point. That is why, you ask why do we have e, what's it matter for? That's why e is important. Do you have to know that to be successful right now? No. Not gonna matter. Again, what you need to know right now is if you have a log base e, that's the same thing as the natural log. Do you guys have questions about this? I used to have questions when I was a kid. Why in the world is log base e ln? How is that natural log? ln, natural log. Why is it not nl? Used to make me mad. The natural log is abbreviated ln. Log natural. That's really close to what it means. I think it's logarithmique naturelle or something. I don't know. I think it's what's the dead language that nobody speaks?
Pig Latin?
Yeah, not pig Latin, but actual Latin. Yeah.
Yeah, it's when you say words. It's when you like put the.
It's when you oink before you say the word. I don't
No,
know.
it's when you
So,
put the first letter at the end, right? Is that right?
talk with me here very quickly about 2 to the x. Do you guys remember what the graph of 2 to the x would look like?
Yes.
What's the domain of 2 to the x?
Infinity, negative infinity to positive infinity.
What's the range of 2 to the x?
0
Zero
to
to
infinity. And beyond.
Okay? A logarithm and an exponential are inverse functions. Remember, we said that this y value could never become negative. I can't plug in an exponent here that would make this negative. So that's why the range here is from 0 to infinity. Because I can't get a negative y. Well, in its logarithmic form, log base b of x, x can never be negative because it's the inverse of the exponential. And what do we do when we find an inverse? We change the x and the y's. So now right here, the range used to be 0 to infinity. Now the domain is 0 to infinity. The domain used to be all real numbers. Now the range is all real numbers. That's what that abbreviation means. Okay? That's shorthand for all real numbers.
Is it just an R with a line through it?
It's like a bolded R. That means all real numbers. This means integers. It's a Z, where that's like bolded in the middle. Rationals. Those are the ones I can remember.
How's it not a Z, Ken?
It's a Z.
It's a greatest than and then less than.
Whatever. You go with your gut, man. So, every one of these logarithms can be found without your calculator. So these would all be non-calculator questions. So, this says log base 2 of 32. Here's what that's asking. Logarithms were a way for us to get the exponent. Logarithms were a way for us to get the variable out of the exponent. So you can think about this is set equal to whatever the exponent used to be. So if I had this, if I had 2 raised to the x equals 32, and I wanted to rewrite this as a logarithm, what would that be in logarithmic form? It would be log base 2 of 32 equals x. That's essentially what this is asking. So when I see log base 2 of 32, the question is 2 raised to what power is 32?
So it's kind of trying to find the exponent.
Correct. 2 raised to what power is 32? 2, 4, 8, 16, 32. So 2 raised to the 5th power is 32. So that means log base 2 of 32 is 5.
What would it, with exponential form, would it look like x equals 2 to the 5th?
No.
Because it asks for it in exponential form.
It'd be 2 to the 5th equals 32.
Yeah. 2 to the 5th equals 32 or 2 to the x. I'll see which one they want written. I don't know if they want you to write in exponential after they do. They want 2 to the 5th equals 32. Questions. I hope everybody's paying attention because this is, like I said, this is going to snowball real fast if you don't pick this up now. I hate it for the people that aren't here. Maybe they'll watch the video. Next, we have, what's this asking? The base, 5, raised to what power is 5?
Here comes the 2.
So that leads to something very interesting. If you ever have a log base 5 of 5, that essentially just simplifies to be a 1. When the base matches, this is called the argument. Whatever I'm taking a logarithm of is called the argument. So when the base matches the argument,
1.
it's 1.
But what if the argument is the square root of that number?
Well, how do you do a square root as an exponent?
1/2.
So 36 raised to what power is 6?
1/2.
1/2. Because what did 1/2 mean? 1/2 is the same thing as the square root of 36. Everybody okay? D, log of 1 over 100. Log? They didn't give me a base.
Base.
Those losers.
10.
It's base 10.
It's like it's a negative number.
It is a negative number.
Like negative 3.
Like not negative 3. This is asking 10 raised to what
negative.
power is 1 over 100?
Negative 4.
It is negative 2.
And why exactly?
So here's the way I would teach you to work this problem. 1 over 100 is the same thing as 1 over 10 squared. And if I move 10 squared to the numerator, it becomes negative 2.
Oh.
So 10 to what power equals 10 to the negative second?
Negative
Negative 2. So again, see all these rules I told you are fixing to be important? No, they
10
are.
to the negative 2 is 1/100.
10 to the negative second is 1 over 100.
Oh, that's like
I-
scientific notation.
A little bit. And I talked about it when we did binary in computer science. If you remember, I did the powers of 10 before we did the powers of 2.
In the flippy do.
Yep. And then we went to 10 to the 0 power. I talked about that being 1. 10 to the negative first was a tenth. 10 to the negative second is a 100th. 10 to the negative third is a 1,000th. Anyways, next. E. I'm taking the natural log of E to the third. The natural log, they didn't give me a base.
10.
So this is natural log means that's a base of E. Right?
Oh yeah,
Because it's ln. Natural log has a base of E. So this is saying E raised to what power is equal to E to the third?
probably
E to
3.
the third equals E to the third.
E to the third equals E to the
E
third.
is equal to E.
So it should be
E to the x equals E to the x.
it should be 3 here.
The X,
So
the X.
watch this, watch this, watch this, watch this. Are you watching? You know, like right here we had log base 5 of 5 and those canceled. What do I have here? I have log base E of E.
Oh, they cancel saying
To
just
the
leave
third.
3.
Correct. So an exponent in the argument can be rewritten as multiplication out front. So what I'm telling you is the natural log of E to the third is the same thing as 3 times the natural log of E. What is the natural log of E? Well, that is log base E of E, which is 1. 1 times 3 is 3. So that's an introduction to some of these logarithmic rules. Do you need more practice with these? Or you want to keep going? Oh, good talk. Thanks so much. I know exactly what you guys are thinking.
Need help with number 2. The tables and stuff. I forgot what happens if you raise something to a fraction.
Oh, it probably just.
Because it doesn't turn into I don't think
So let's just do the first table. Plug in -1 for x. What is 3 to the negative first?
1/3.
Is it okay with that? What if you plug in 0 for x? 3 to the 0.
1,
What if you plug in 1 for x?
3,
2 for x.
9,
3 for x.
27. I know that one, but the
Now let's plug in 1/3 for x here. 3 raised to what power is 1/3?
negative 1.
Three raised to what power is 1? 3 raised to what power is 3? 3 raised to what power is 9?
2,
3 raised to what power is 81?
9, 4.
Oh yeah, 4.
Okay, I get it now.
What is the relationship between f and g?
Wait, can you answer one of my questions really quick? What happens if you raise something to a fraction? Is that supposed to be one of our rules?
You rewrite it as a radical.
I remember now. X to the 1/3 will be cube root of x, right? What if it's like, yeah, for the denominator goes on the outside, and then the numerator goes above the x, so it's like x raised to that power, raised to the numerator.
Yeah, x raised to the numerator, and you're taking this root of it. What's the relationship between f and g? Here I plugged in -1 and I got out a third. Here I plugged in a third and I got out
They're
-1.
inverses.
Here I plugged in 0, got 1. Here I plugged in 1, got 0. They are inverses of each other. Normally you would have just had that lesson right before this. Right? That's why they're wanting to make that a big deal. Anytime I just change the x and y values, they are inverses. So what's the relationship? Inverses. How can you tell? By looking at the table. You have switched.
X equals what?
You switch the x and y values. That's what I would say. Let's see what A plus says. Inputs and outputs switch. Okay. B, find g of f of x and f of g of x.
This might be where I'm good.
Yeah. So I'm going to do these because it's been over a month since we've done this. But what did g of f of x mean? It means I'm going to plug in f of x, which was 3 to the x. So what was g originally? G was log base 3 of x. But instead of saying x, now I'm going to say 3 to the x, right? I'm plugging in 3 to the x for x. That's what f of g of x means. So now what do I have? Log base 3 of 3 to the x. The base and the base here are the... So I can move the x out front and multiply it. So that becomes x times log base 3 of 3, which is just x. Everybody's okay with that? I would normally write that down the page, but I don't have room right here. So now let's go the other direction. What if I had f of g of x? So this would be f of log base 3 of x. So what was x originally? X was 3 raised to the x. But now instead of saying x, I'm going to say log base 3 of x.
I got the g of f of x, but I don't get the f of g of x. Wouldn't it just be 3 to the x times log 3?
Say that again. I was thinking of something else. I'm trying to give you what I'm fixing to say here, but I'm listening to you.
I understood g of f of x, but I don't understand f of g of x. 'Cause-
F of, what was g of x?
So g of x is log to the
Log
base
base
3
3,
of x.
log base 3 of x.
Okay, and then
And I'm plugging this into the function f.
so
The function
three
f
x.
is 3 to the x. Well, now instead of saying x, I'm saying log base 3 of x. This got plugged in where the x used to be.
So 3x.
You don't know how to simplify this yet.
Yeah.
That's what I'm working on. I think it's come up with the
I think
words.
that's why I'm confused.
Yeah, so just give me just 1 second. Okay, let's see. I'm going to try to explain this in words. I'm trying. This is not one of my favorites to do in words. Think about just the exponent here. What's this asking? This is saying 3 raised to what power is x? Right? 3 raised to what power is x? 3 raised to what power is x? That's what's being asked here. So what is the answer to this question? Like looking here, which part of this is the answer? 3 raised to what power is x? The answer would be whatever this question mark is. Right? That's the thing I'm trying to find, is the question mark. So log base 3 of x is the question mark. What did the question mark answer? The question mark was the answer to 3 raised to what power gives me x. So now then, the answer here is a question mark. And so what is 3 raised to that question mark? I told you this is hard to explain. Let me try it again. If you look at this on its own, forget it's part of an exponent first. It asks the question, 3 raised to what is x? I don't know what x is, so I don't know what the question mark is. Okay? Let's change that. Let's give a very real example. See if that works. Let's pretend like we knew this was 9. Okay? Let's pretend like we knew that was 9. So this would be asking 3 raised to what power is 9? We know the question mark then is 2. So then the answer to this would be 2. So now the thing that's left is 3 to the second. What was 3 to the second? 9. Well, what was 9? X. Right? I just made that up as the x. So if you can think the same way, 3 raised to what power is x? I don't know, but the answer is this question mark. So what is 3 raised to that question mark? X. Because the answer was 9 when it was 9. Now it's question mark when it's question mark. Is that mind confusing? Yes. Do you have to know it at that level? No. Here's all you have to know. If I have 3 raised to the log base 3, that cancels. Okay? Equals x.
Well, we knew they were in there, so we knew they were in there.
Yes.
But
I was trying to explain the thought process behind it. I'm probably not the best at explaining that. You could find a YouTube video that does a better job. I convinced myself, let me do the 9 again, now that you know the answer. Okay? Let's pretend like this was 3. Let's get that down. That was good. Let's go 3 raised to the log base 3 of 9. So this is asking 3 raised to what power is 9? 2. So the answer to this is 2. So this becomes 3 to the second. What was 3 to the second? So what essentially happened? 3 raised to the log base 3 canceled and left me with 9. Okay? I tried to explain it with just generic. That's probably not the best way. I probably should have done this first. Okay? Complete the following sentences with added... Oh, gosh. I don't want to do that. As the inputs of F grow... Oh, God. I don't even care. The answers are additively and multiplicatively for the first one. Then the second one is multiplicatively and additively. I could not care less about that.
is that going to be on the test?
I've never seen that before in my life.
So I'm just going to cross the big X.
I'm okay with that. You guys see my pencil?
See, I believe it. I see it.
All right, what did an exponential look like? Exponential graphs looked like this. And how do we find inverses graphically? We can reflect it over the line y equals x. So you see how this logarithmic graph is just a reflection of an exponential graph. So logarithmic graphs have a vertical asymptote, whereas exponentials had a horizontal asymptote. Right? So when I look right here, what's the domain of this logarithmic graph? 0 to infinity. What's the range? What's the lowest y value? Negative infinity to positive infinity. I know it looks like it's going to start growing more slowly, but it never has a cap. There is no horizontal asymptote. Right? It just grows very slowly, but it will continue to grow forever. This is what happens when the A value is positive and the B value is bigger than 1. Okay? We will not do any logarithms where the base is negative. It's not allowed. Because if you do, that would be asking the question, negative 2 raised to what power is x? Well, we require x be positive. Because the x's here used to be the y's of an exponential. And what was the requirements for the y's of an exponential? From 0 to infinity, right? The y's could not be negative for an exponential, which means for its inverse, the x's cannot be negative. And so because these x's cannot be negative, I can't get to every possible answer. It's not worth, again, not my favorite to talk about. Can we talk about limits with this? Like if you look at this, what happens as x approaches 0? Do you guys remember what the plus sign means here? It's a one-sided limit. This means we're approaching 0 from the right. So as we get closer to 0 from the right, what's happening to the y values? They're going towards negative infinity. And then the right-sided limit. As I go to the right. So this is the limit as x goes to infinity. So what happens when the x's get really big? The y's also get really big.
Okay, something blows my mind. So you see that the graph A?
Mm-hmm.
X is obviously growing faster than B and more. Like it's growing a lot more than B.
Yes, the x's.
How do they both end up equaling infinity?
Infinity just means that it's going to continue to rise.
Because there is no last number, right?
Correct. So as the x's get really, really big, the y's are going to still be going up. Now, you're right. Like when x is at 1,000,000, the y's may only be at 1,000. Right? You know what I'm...
Yes.
But as the x goes up, the y still goes up. That's all that matters. There is no cap. All right. I'm So this is all going to be looking at stuff that hopefully we know how to do already. They say that they'll let you use your calculator on number 3. For some of them. So we're going to do as many as we can without a calculator on 3, and then we'll add the calculator. Let's just start at number 1. Find the value of A that a base of 2 must be exponentially raised to in order to obtain an 8. So this says 2 raised to A equals 8. A has to be 3. So this statement then is 2 to the 3rd power equals 8. I want to take this exponential statement and write it as a logarithmic statement. So we're converting from exponential to logarithmic. Log base 2 of 8 equals 3. Now we're given a new statement. What if I had b raised to the a equals c? How would I write that in logarithmic form? Log base, it's base b of c equals a. Do we feel comfortable enough doing that? You got to do that over and over and over. So I want to make sure that you guys know how to do that. Two, we're going to graph an inverse. So right here's a graph of 3 to the x. And I know g is the inverse of that. So what do I do when I find an inverse? We change the x and y values. So if 0, 1 was a point of f, then that means the point 1, 0 must be on the inverse. If I have the point 1, 3, then that means 3, 1 must be on the inverse. And negative 1, 1/3 means that 1/3 negative 1. And so this would be a sketch of the inverse. Remember, anytime you have a graph and you graph it and its inverse, it's a reflection over the line y equals x. You can see the dotted line I drew there. So it's a reflection over that. That should also help you visualize. Okay, let's simplify as many of these as we can without a calculator. The first one says log base 2 of 64.
No, it's 6.
No, it's 7. No, it's 8.
6.
How'd you get that?
Because 16 times 2 is 32. And then 32 times 2 is 64.
Okay.
2 to the third is 8, 2 to the fourth is 16.
Okay.
2 is 32, 2 to the sixth is 64.
This is asking 2 raised to what is 64. So you just have to do your powers of 2. So 2 to the first starts at 2, 4, 8, 16, 32, 64. Right, which would be 6.
Good, easy way to do that.
What?
You don't know your powers of 2?
I mean, of 2, yeah.
Yeah, I mean they're not gonna give you hard ones other than like they're not gonna go past the third or fourth power
No.
on anything but 2. I mean, this is probably about as high as they'll make you go with 2. 6, maybe 7th. When you look at the next one, log base 4 of 120. So this is 4 raised to what is 120?
It's going to be a decimal.
Yes, 4, 16, 64, and then 64 times 4 is 256. Right, so I can't get 120. So this is one that they would want you to use a calculator on. All right, I figured out it's going to be between 3 and 4. Right, so it's going to be 3 point something on my own. but we'll have to use a calculator to figure it out.
3.8.
Go to 3 decimal places. Remember, pre-cal, we go to 3, so it's not going to be 3.8. I don't think it's going to be that high. I think it's going to be like 3.2 something or 3.3
How do
something.
we find that by using a calculator?
Huh?
Put it in your calculator.
You do square root.
Okay.
You do fourth root of 120.
Let's see. You may not can do it on these. This is okay. I'll show you how to simplify it in a second.
Oh.
I can always whip out the Casio.
Math? No, we don't want to use the Casio.
But it's got that log button.
It does, but you can't use it on the AP exam.
Is it bad?
Log box.
You're only allowed to have graphing calculators. You're not allowed to have anything but a graphing calculator.
It's Chucky roasted.
Hey, so you put 4, 5, 3.
Can't use that.
But
It's gotta
actually,
be this one.
well, my other one's dead, so we gotta make do with what to do.
Correct.
You gotta find
So
the
you
log.
can't do.
You can't change the
You
base.
can't change the base on there. So I'll show you how to do those later.
Log box
Okay.
box.
You-
Log box box.
If you go to math,
I went to math and then I just scrolled down and it had more days on there, I didn't change it.
there it is. Very good. Hey, click math. Thank you. Math, and then A.
3.45.
Hey, where's the A?
Where's
Silly now.
where's code 3?
Cool with that.
3.453.
Okay.
That was closer to 3.5 than I thought it would be.
3.453.
3.453. Which, if you rounded to the nearest tenth, would be 3.5. Which I did not think it would be that high.
Jack Riley was correct, but he just didn't know it.
But
Okay, the next one. We could do this one without a calculator.
yep.
3.
It is 3.
That at 8, 16 times 4.
Is okay with that? What about the next one? 4 raised to what power is 1/5?
Log.
Well, 4 raised to the negative first would be 1/4, right? So this is a little bit smaller than that. So I'm expecting something a little bit more than -1, but I can't do it without a calculator. So I'm going log base 4 of,
Negative 1.161.
No, 1.
oh my gosh,
Negative 1.161.
negative 1.161.
Negative. Yeah, I kind of like this.
The next one, log base 2 of 26.
That's not a calculator one. You gotta use the OG.
4.700.
4.707.
Okay. Log base 6.
1.613.
1.613.
The next one's one you can do without a calculator. Log of 10,000.
Just count them. Count them up.
Count what?
0.
That's correct. If you ever have log base 10 of a power of 10, just count how many zeros there are. So there's 4 zeros. The answer here would be 4. And then we should be able to do log base 6 of 1/6 without a calculator.
Negative 1.
Because you just flip it.
Uh-huh. Questions?
Like 601, you just 106.
That's right.
don't got an equal.
Did you?
Are you gonna get the black one?
Probably. Yeah, that's fine.
3.5 business.
Probably. Dude.
Okay, so this is something, you're not going to see a lot of questions like this, but being able to tell that it is logarithmic. So for me, I'll look up, I'm going to look up what they say.
X equals 5.
My answer here would be, well, x is not equal 5.
The thing, the example.
Yes, we're raising powers of 5. So this is log base 5 of x. Right? That is the equation. For me to be able to tell that this is logarithmic, here's my thought process. I look at the y values. The y values keep going up by 1. So that's a common difference of the y values. How did we tell if something was exponential? If you'll remember, we had common ratio of the x's, and then we could divide the y's. Well, for logarithmic, I would do the opposite. I would make sure there's a common ratio of the y's, which there is, or a common interval, I guess I should say. We keep going up by 1. And then if I multiplied or divided here, 1/5 times 5 is 1, times 5 is 5, times 5 is 25. That is my thought process, but I don't know if that's what they want you to say. So let me get their answer up, and I'll just show you what they said. If I can get it to load. We're not that far yet. That's close to where we're at. That's close. Here's their wording, okay? The input values change proportionally as the output values increase in equal length intervals. Or you could say the outputs change additively as the inputs change multiplicatively. I do not remember seeing a question like that last year, so I would not get to. I don't remember seeing anything like that.
So we have to give an explanation on it. Can we just say because it is?
That's not gonna work. No.
On the test?
Yeah, that
I
won't work.
normally just look at the explanation. I don't know the explanation. I'm just gonna give an explanation. And you guess the answer. Sometimes it's right.
5. Oh, sorry, I don't know what I'm doing. Shouldn't be taking a picture. Suppose that G and F are inverses. What would be F of G of X and G of F of X?
F of G of X.
X and F of G.
Whenever you build a composition of functions that are inverses of each other, it should simplify to be X.
Oh. How?
Well, we learned that way back
Wait, is the
in
F of
Canvas
G
2.3.
F, do they just cancel? Because they're opposites.
If you want to think of it that way. No, that's not how it normally goes, but don't do that. table to the left gives values for a function for select values of x. There's a missing value in the table in the last row. Sophie observes the function is logarithmic because there's a multiplicative change for the inputs as the outputs increase over equal length intervals or grow additively. She decides the base of the logarithmic function is 4 and that log base 4 of 1 over 64 equals 2. What is wrong with her reasoning?
It's backwards and it's cut in half and then flipped to the negative.
No, it's just backwards.
Well, like the square root of 16 is
Right.
4, and then half of 4 is 2, and then it's flipped to the negative. The square root of 4 is 2, cut in half is 2, and then flipped to the negative is 1, flipped to the negative is negative.
So what is the base? The base is not 4. That's her problem. How did I know the base wasn't 4?
Because 4 to the negative 1 is not.
Not 4.
It's negative 4.
It's not negative 4.
It's not.
No, it's positive 4.
It's not positive 4.
4 to the negative 1 is not 4.
What? But if you,
And 4 to the first power is not 1.
but if you double it,
The base should be 1/4, not 4.
Yeah, it's 1/4.
The base, that's what I just said. Y'all didn't say it. You kept saying
Because
negative
it's to
4.
the first power.
And then you'll say, yeah. Correct. Because when I raise it to the first power, I get 1/4. Well, so what to the first power is 1/4? 1/4 to the first power is 1/4.
oh,
If I raise 1/4 to the negative first, you should get 4, right? Flipped.
you flip
version.
the negative.
Okay, so hopefully you guys acted like you could rewrite these things, that it wasn't any issue with the simple versions. Well, now we're growing to these 3 properties. These are the last 3 properties we'll learn. That's not true. These are the biggest 3 properties we will learn. Huh? We're fixing to get to them. That's why I was looking.
So we haven't learned any properties.
You have.
But we just.
You've learned how to change from exponential to logarithmic, logarithmic to exponential. We also should have practiced rewriting bases. We did things like this, right? 4 to what power equals 16? And then I showed you that you could rewrite this as 4 to the second. Did we work on did we work on this? If I have 5 to the 3x, we could write that as 5 to the third to the x. And then we talked about if we have 5 to the x plus 7, we could write this as 5 to the x times 5 to the 7th. So that's the stuff that you need to know now at this point. We need to be good with that. And now we're fixing to add 3 more properties, which is the product property, the quotient property, and the power property. Okay, here's my Sam Mountain definition for all of these. Okay, just looking at this, you see this is x times y. This is called the argument. Have I told you guys that before? What's inside these parentheses is the argument. Whenever I have something multiplied in the argument, I can rewrite that as addition of logs. So right here, log base b of x times y is the same thing as log base b of x plus log base b of y. So multiplication in the argument can be rewritten as addition of logs. This also goes in the other direction. If I started with addition of logs with the same base, I could rewrite that as multiplication of the argument. Okay? This goes in both directions.
Oh, kind of like how you did it, 5 to the x plus 7, you did 5x.
It's very similar. Because what is this? Remember, ask the question. Log base 5 of 125.
You could rewrite that as log base 5. Log base 5 of 5.
6.
We could write this as, according to this rule, 125 is the same thing as
Log base.
25 times 5. You okay with that? It's multiplication. So this would be log base 5 of 5 plus log base 5 of 25.
Technically, couldn't we do, it's the same.
And we could do it again here. 25 is the same thing as 5 times 5. So this could be log base 5 of 5 plus log base 5 of 5 plus log base 5. I would not do it on this problem, right? But I'm just showing what you can do with these rules.
So you're
Because-
telling me, wait,
What is log base 5 of 5? 5 raised to what power is 5?
1.
Anytime the base and the argument match, it simplifies to be 1. Base and the argument match simplifies to be 1. Base and the argument match simplifies to be 1. 1 plus 1 plus 1.
But we already knew it was 3.
No kidding. I told you I wouldn't do that on this problem. I'm just showing you that it works. I'm trying to give you an example of why you can do it.
Could we do log base 5 of
Wait,
125
5 to the-
equals log base 5 of 124 times 1? Log base 5 of 1?
No. Why would I change it to addition?
I don't know, because that works.
It does not work. That would be addition of the argument. Do I have anything about addition of the argument? No. This is multiplication of the argument. I can rewrite it. There's no rule for addition of the argument.
But it is a true statement.
Sure, but I can't do anything with it.
Just use the...
I like multiplication of the argument, or I like division of the argument. So, okay, let's look at this example. You see how they did log base 2 of 5x. This is a more useful time to do it. I know we did it with 125 and a base 5. But here, this is multiplication in the argument. Multiplication in the argument can be rewritten as addition of the logs. Log base 2 of 5 plus log base 2 of x. Why might I? Because now I'm closer to getting x by itself.
We know what log base 2 of 5 is.
We could figure it out. It's just a number.
Yeah.
Correct.
Log base 2 of 5.
But we didn't know what log base 2 of 5x was.
Everybody understand this rule? Look here. This is division of the argument. So if multiplication of the argument was addition of the logs, division of the argument is subtraction of the logs. It's always the numerator minus the denominator. Always the numerator minus the denominator. So this is log base b of x minus log base b of y. And remember, this can go the other direction, right? So if I have a logarithm that's being subtracted, I can rewrite that as division of its argument. Okay? And then the last one, if I have an exponent of the argument. Exponents of the arguments can be rewritten as multiplication in front of the log. So I'll say that exponent can come out front.
We kind of knew that.
We talked about that earlier. We talked about canceling out. Maybe I did that in here. And we were just left with the exponent. Remember we had that ugly... And so, same idea. If I had log base 5 of This is saying 5 raised to what power equals 5 to the x power? What does the question mark have to be here? X. Right? That's what it has to be. What you can do, according to this power property, I can take this exponent of the argument, move it out front of the log. So this becomes x log base 5 of 5. Well, what is log base 5 of 5? 1. What's 1 times x? I get the same answer, right, without having to think through it. Again, I'm doing it on a very simple scale right now because that's where we've got to make sure we understand. I want to let you try to do these on your own without just watching me do them. So, but I want us to kind of work together through them. So I want you to try A, and then in a minute, I'll see if you got the answer to A. Our goal on every one of these is to end with a single logarithm. So currently it has 2 logarithms, question A does. I want to finish with a single logarithm.
So, you're turning it into those.
If that's the way you want to think about it. Are we finished with A?
Yes.
I have addition of logs, which means I can write this as multiplication of the argument. Finished.
Yes.
You guys okay with that?
I got another B too.
You've already done B? Is everybody finished with B? I'm giving you too much time? Okay, what is B?
Log base 3, 5 over Z.
I agree. Log base 3 of 5 over Z.
Log base 3 over 5 over z.
What about C? Log base 10.
It's just called log, right?
We could just call it a log because it is a base of 10.
Log X over 5 over Z.
X over 5 over Z.
5x over z.
So
X over 5.
So, have you ever seen this before? Do you ever want to see that again?
Yes.
I saw it on my ACT and I was like, man. I just shut my eyes and clicked one. Or circled one.
How is it X over 5 Z? I don't understand.
Okay, I'm going to show you 2 ways to do it. Then I'm going to tell you how I do it. If you had this ugliness, which, gosh, I would never want to write that.
Technically, isn't that correct?
Can be. But they're not going to accept that form. Nobody in their right mind is going to accept that form.
So you wouldn't accept this?
I would not take that form. That would be wrong. That's wrong. I don't care what you like, that's wrong. Okay? How did this start? We started as an x, and then we made this x over 5, and this was our answer.
No.
And then we put this over z.
Yes.
So you could make this a fraction over a fraction. So this could become x over 5 divided by z over 1. Let's go to 4th grade math, 5th grade math. How do you divide fractions? Oh my gosh.
5z.
And multiplied by its reciprocal. What is x times 1? 5 times z.
So you keep flip change.
Or you can just.
No.
That's, you keep the one left.
Keep, change, flip.
It's easier to remember like keep flip change.
Or you can just.
No. So that's not what I would do. Me not do that. Here's what me do.
You pick
This one is positive logarithm. That argument goes in the numerator. Negative logarithm, that's the coolest guy we know. I mean, my gosh, why does anybody want to sound like that? Negative logarithm, that goes in the denominator. Negative logarithm, that goes in the, that's all I do.
Once they're all negative, do they all?
Then they would all go to the denominator.
And
Might just be.
There'd be one left in the numerator.
it'd be 1 over x.
1 over
5z.
teeny, 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 teeny.
1 over x, 5z.
5xz.
5xz. Okay, one thing we've not talked about yet.
I gotta get one.
Every one we've done so far, there have been no numbers in front of the logarithms.
There's been no coefficients.
Correct. All these rules that you just went over, they only work when there are no numbers in front of the logarithm. So when I look here, this is different. 3 log base 2 of x. I can't do any of these fancy rules until I get rid of this 3.
So we're gonna divide by 3 on both sides.
There is no other side.
Each set it equal to 0.
That's correct.
You can go.
The power rule. I'm going to move this 3 back as an exponent of the argument.
Yes.
So this becomes log base 2 of x cubed minus log base 2 of y.
Cube.
Now I have logarithms.
Wait, you don't cube both of them?
No.
No,
Oh,
it's
God,
only
God,
on
God,
one
God.
side.
Now I have logarithms with no numbers in front of them. So now I can do the subtraction rule. Subtraction of the logarithms can be rewritten as
So it's log base 2
Of x
of
cubed
x
over
cubed over y.
that's what it is.
Oh, I don't like it.
It's easy. Better late than never, better late than never.
That was the best song of the day.
What about E?
Okay, with E we gotta change.
Is it log
We
base
got-
7 of 4a squared over b?
I have no idea. I've not done that for yet.
Okay.
Log base 7 of a squared.
Execute the 2 in front.
Log base 7 of b to the 5th plus log base 7 of 4.
That's where the wild things show.
So for me, from here, I could go log base 7 of 4a squared over b to the 5th.
Yes.
Is that what you said?
Yeah.
Then yeah, that's the answer.
4a squared is part of the quadratic formula.
Minus 4ac.
Oh, 4ac.
That's going to go well when you get to the quadratic formula. I can already tell. That's going to go
I
great.
have some socks that have quadratic formula.
You going to wear them on test day?
Yes.
Smart.
Those Brody Kenny Minecraft songs.
No, I had to sell those socks.
So this last one, me personally, I think this is in a fine form. Like there's no way I could simplify this. I think that's as simple as it could get.
It's kind of suspicious a little bit.
But just me thinking, and I've not looked at what they want me to do. Let me show you. I've thought of a way that we could simplify it. I do not like this. Like I would not do this naturally. Okay, this is just me forcing this to happen. How did I get this to be just a 2? Well, I could rewrite it as a logarithm problem. Logarithms are the answer to we will ask base raised to what equals some number. And so if the answer to the question mark was 2, that would simplify to be 2. So again, this is not, I don't think that they're going to want you to do this. This is me just making this up. I could write 2 as log base 6 of 36. Can you wrestle with that? Does that make good sense? This says 6 raised to what power is 36? 2. This would simplify to be 2. So I could write 2 as log base 6 of 36 plus log base 6 of x. And now I have addition of logs that I could write as multiplication of the argument. I don't know why I wrote it like it was going to be a fraction. Now let's see if that's what they wanted. They have given the answer of log base 6 of 36x. So that is what they wanted you to do. Okay? I've never seen a problem like that before. Just, again, being honest with you. So try this one. Last one we'll do. I'm given log base 3 of x squared over y. So now I'm given the single logarithm. And I want to know which one of these is that equivalent to.
Z.
Z is more this.
C. Z, not C.
So first thing I would do, I have division of the argument, which means I could rewrite that as subtraction of 2 logarithms. So this is log base 3 of x squared minus log base 3 of y.
You didn't hear my explanation.
Is that an option?
No.
It's not a choice. So the next thing I would do is I would get rid of this exponent of the argument as multiplication of the log. 2 log base 3 of x minus log base 3 of y. Is that an option? Yes, that's z, as we've all heard said so many times.
No, look, this is my thing. So we know we got x to the square in the numerator, right?
Okay.
So we know we're gonna have a 2 out in front.
Okay.
So we know we're gonna have a 2 out in front of the first one.